Okay, I'm back. On the next slide you see this. We have a short little lab that we normally do in class. It's kind of a fun lab, and it produces some rather interesting results. What we do here is we measure the resistance of a copper wire, and here's a copper wire in a coil, and it's set up so that we can immerse this into ice water, boiling water, and liquid nitrogen, and then we use a multimeter that this is hooked up to record the resistance. So if I turn this on to, whoops, I want resistance, or here, whoops, there we go. So if I turn this on here, we see that at room temperature anyway, the resistance of the copper wire, it looks to be like 93.8 to 93.7 ohms. So in class we would measure the temperature, the room temperature, which of course is around 20 Celsius, and we take measurements in ice water, boiling water, and the fun one is liquid nitrogen, because you put this thing in liquid nitrogen. Of course, the liquid nitrogen boils for a long time, and while that's happening, the resistance, you can just watch it steadily drop. It's really kind of fun. But what I'm going to do is use the data that we took last year, because guess what? We don't have any liquid nitrogen. So here's the data that the students collected last year, and they read the degrees Celsius from the multimeter, and what they had for room temperature was 20.8 degrees Celsius, and then you just convert this to Kelvin, because that's what we're going to want to plot. This is 293.8 Kelvin. For boiling water, they measured that temperature to be 99.5 Celsius, so we get 372.5 Kelvin. And then putting the coil in an ice water bath, that's temperature was 0.1 degrees Celsius, so this is 273.1 Kelvin. And then in the liquid nitrogen, which is minus 196 Celsius, or 77 Kelvin. Now here's the resistances they got. Let's do those in purple. At room temperature, the resistance was 96.6 ohms, fairly close to what that particular meter was reading here just a minute ago. In boiling water, they got 125.0 ohms. In ice water, you have 88.4. And in liquid nitrogen, it came out to be 9.8 ohms. Okay, the first thing you're asked to do with your data down here is, given that the diameter of copper wire, this particular gauge is 0.0056 inches, use your value of resistance at room temperature and the resistivity of copper, which is given here, to calculate the length of the wire in the copper coil. So for this, first you got to do some unit conversions. We have that the diameter is 0.0056 inches. This works out to be 1.422 times 10 to the minus 4 meters. And now we can use the fact that the resistance is rho L over A, and solve this for L. L is equal to R A, that's an A, over rho. Put in the numbers that we have. Everything is in MKS. We're using the room temperature resistance here, 96.6 ohms, and I get that the length is 90.2 meters, or if you want, 296 feet approximately. And that is around correct. The devices were made where they're used about 300 feet of that copper wire. Now, notice that the length and the area of the wire doesn't change, but the resistance changes with temperature. So what we're really looking at here is how resistivity changes with temperature. Maybe we should have another column here with resistivity, because that's what's changing. But what's interesting about this is how it changes. The next thing on this lab was to use the grid here and plot the 4 data points that we have. We have resistance on the vertical and temperature on the horizontal. So the temperature ranges up to about 3, whoops, I wrote that wrong, didn't I? 372. I think I said that, but it's 372 is the temperature of the boiling water, about 100 degrees Celsius. So we go almost to 400 Kelvin and then down to 77. So I broke this up this way. I said that's 200, 100, 150. No, I want that to be 300. Remember, I only have one take to make these videos. So there's 400. Now in resistance, we'll take that to be 0. And we go up halfway, we'll take that to be 100, and that to be 200. So we only have 4 points here. Let's see what they look like. So for the liquid nitrogen, the temperature is 77. The resistance is just under 10 ohms. So that's going to be right about there, because the line is 20. For the ice water, we're at 273 Kelvin and about 88 ohms. So 273 is right about here. This is 80. We're almost to 90, so right about there. Room temperature is 294 Kelvin and almost 97 ohms. So 294 is right about here, and about 97 ohms, very close to there's not a big difference between the ice water temperature and the room temperature. Now the boiling water is 372 Kelvin and the resistance is 125 ohms. So 372 is right about here, and I come up here 100, that's 120 there, 125. So there's the 4 data points. Now, it asks down here, how would you describe this data? How does resistance depend on temperature? Well, I only have 4 points, but they sure look like a straight line, don't they? And if you plotted this as resistivity, you would also have a straight line. So, we have something that looks like approximately a straight line. And what we would say is that resistance is proportional to temperature. The proportionality constant would be the slope of that line. Now, be aware that between 0 and 77 Kelvin, this doesn't come down to 0 here. It's going to do something else in here at lower temperatures. Now, the next question says, based on what we've done in class, how should resistance depend on temperature? Theoretically. This would be the theory. And of course, this is the experiment. We just made the measurement. Actually, we did it last year and used their data. Well, this is pretty tough reasoning, and I wouldn't expect many of you in the class to be able to do this, but here's how it works. We know that resistance is proportional to resistivity. R is equal to rho L over A. So we're just going to work with proportionalities here and see if we can get the dependence. We know, if you look back at what we did on Monday, you can see that rho is proportional to 1 over tau. Now, tau is the mean time between collisions. We may have seen this on Monday as sigma is proportional to tau, but remember rho is 1 over sigma. Tau, the mean time between collisions, is proportional to some average distance traveled between collisions. That's the mean free path. We didn't use mean free path here, but we did use it back in chapter 20. So tau is going to be proportional to some lambda divided by some average velocity. Let's say VRMS. So this says the time between collisions is proportional to the average distance traveled between collisions divided by the average speed. Now, think back to what we did in chapter 20, where we had the root mean square velocity. And what we had back then was that VRMS is proportional to the square root of the temperature. Because we had the equation VRMS is the square root of 3kT over m. So we have VRMS is proportional to temperature, tau is proportional to lambda over the temperature, so tau is going to be proportional to temperature, and you run this the whole way back through the proportionalities, and what you get is that R, the resistance, should be proportional to temperature to the 1/2. So this is what the theory predicts. R is proportional to T to the 1/2. And the question here is, does that agree with your plotted data? And the answer, of course, is no. Our data, which is pretty clean data, says that the resistance, in fact, is directly proportional to the temperature, at least in this temperature range. So, we have a problem here, that the theory and the experiment do not agree. And really, remember, this is in the resistivity, not just the resistance. The theory that we have here says that the resistivity should go as T to the 1/2, and we'd expect a curve more like this or something. But this is what we have up here with the experiment. So what's going on here? Well, what's going on is this. The electrons are not really in a Maxwell-Boltzmann distribution. This is another one of those subtle experiments that reveals that there's something else going on at the microscopic level that we haven't accounted for. And of course, that's quantum mechanics. Electrons are in a solid are not in a Maxwellian distribution. You have to use the quantum Fermi-Dirac distribution, and that gives different average speeds. Also, the quantum nature of the electron is important in how it interacts with the ions. So there's a lot more going on here than we can account for with our theory. So if you do the quantum treatment correctly, you will get that the resistivity is proportional to the temperature in this temperature range. So it's a nice experiment, and it does show us, again, a case where classical physics breaks down. Now, I'm going to put two of these slides on the video, or on the PowerPoint that I post, one blank and one with the explanations on it.